Alright, let's talk about the PID controller. Before we dive into the PID controller, we need to know that it's made up of three parts. One is P, one is I, and one is D. These three work together. Let's start with the simplest one, P. When we're doing simple control, we always have a target we want to reach. For example, if we're controlling temperature, say we want the water heater to reach 60 degrees. We set the target at 60 degrees Celsius. Another example is cruise control in a car. We want the car's speed to stay at 100. So the controller needs to figure out how to get our car speed close to 100. Once we have a target, we have a target value. And of course, there's also our current value. Let me give you an example. Say your car is getting onto the highway from an on-ramp. Your car's current speed is 30 kilometers per hour. On the highway, the speed limit is 100 kilometers per hour. So you realize you're still 70 short of 100. What would you do? You'd floor the gas pedal, right? Get the car up to 100 fast, because driving at 30 on the highway is super dangerous. After you floor the gas, the car starts accelerating faster and faster. When the speed reaches 90, what happens? Your foot starts to ease off. You slowly release the gas pedal. The acceleration decreases because we're already close to 100. No need to push so hard anymore. If we draw this on a chart, you'd notice when we're far from the target, we press hard on the gas. When we're close to the target, we slowly release the gas, reducing the throttle. For example, our target is 100, and we're currently at 30. How far are we from the target? That's 70. Where does 70 come from? It's 100 minus 30, right? And if our target is 100, and we're already at 90, how far from the target? Just 10. When we talk about how much distance is left, it's simply subtraction. A simple subtraction gives us the gap. Now, here's something interesting about control systems. The input and output are usually not the same thing. For our car, the output is speed in kilometers per hour. But what's the input? The input is the gas pedal. And since the pedal doesn't really have a unit, let's say the pedal range is 0 to 10, but the output speed goes from 0 to 100. The pedal only goes up to 10. Clearly, you can't just plug the air directly in. If the gap is 70 and you feed that straight into the pedal, the car would fly to the moon. So, if we want to convert this gap into the pedal's range, we need to multiply by a ratio. Let's say the ratio is 0.1. Then 70 times 0.1 gives us 7. And 10 times 0.1 gives us 1. That fits the range pretty well, right? This is the proportional principle. When the gap is large, we press more. When the gap is small, we press less. Pretty simple, right? That's the proportional controller, just a subtraction. And then a multiplication, and you're done. That's the proportional controller. In code, it's also very simple. When writing a P controller function, the function first calculates how far we are from the target. Like I said, it's just subtraction. Target minus the current value and we call that the error. Then the error multiplied by a ratio gives us the output. The output controls how much we press the pedal. That's the simplest framework of a P controller. I've also made a simple interactive web demo for this. Just scan this QR code and you can try it out. That's why I like using web pages for these demos, because I want you to interact and play along, not just watch. It's really fun. Here, you'll see I've set the proportional controller to 2.0. See the 2.0 in the bottom left. The red line represents our target, which is 60. The blue line is our current position, the actual value. When we run it, you'll see it slowly climbs up, but then it drops, goes up again, drops again. After some time, once it stabilizes, you'll notice it never reaches our target of 50. It settles at 35 and stays there. Your car's speed never actually reaches 100 number dust. It stabilizes at a value lower than 100. This phenomenon is called steady-state error. This is where the eye controller comes in. It adds up all the past errors over time. As time goes on, this accumulated value gets bigger and bigger. Once it gets large enough to make a difference, it gradually pushes the gas pedal for us. In our P controller code from before, the integral part keeps adding up the error. The plus equals operator means keep adding. Integral equals integral plus error. In code, you'll sometimes see plus equals. And since it's time related, we usually multiply by the time interval. Then we add this integral result to our output. As errors keep piling up, the integral slowly grows bigger and bigger because the loop keeps running. Once it grows large enough, it starts to have some force, and our gas pedal pushes just a little bit more. Let's see the effect after adding I. Here, we'll set I to 0.1. Let's restart. You'll see that after P oscillates a few times, the I slowly brings it closer to 50. But near the end, it still creeps up very slowly. Let's see how long it takes to reach our target of 50. Okay, we can see it takes about 85 seconds. It took a full 85 seconds for our P and I controller to reach the target of 50. Can we make I bigger to speed things up? Sure, let's set it to 0.3. You'll notice it catches up much faster now. Around 30 seconds, maybe 40 seconds, it already reaches 50. So you might think, great, let's crank up I to a really large value and it'll be even faster, right? Let's see if that works. And you'll find it's not quite what we expected. When it gets too large, it keeps accumulating errors and it starts oscillating. It can't reach a stable state anymore. When the I controller is too big, you get oscillation. How do we tune these values? We'll cover that later. For now, let's keep going. After adding P and I controllers together, you see lots of swinging back and forth. Hard to reach stability. The D controller is here to reduce this oscillation. The change in error represents the short-term trend. I predicted your prediction, so I hit the brakes for you. I know that sounds tricky, but really, it's just this error minus the previous error. The decontroller is simple to write. Take the current error, subtract the previous error. That's the derivative. That's the core of the derivative controller. Since it's time-related, we divide by the time interval. Because some CPU runs faster with more iterations, some run slower with fewer. If we don't account for time, faster systems compute more, slower ones compute less. That's not right. You need to factor in the time interval. So whether your CPU is fast or slow, or the system is busy or idle, the time between each cycle is different, which causes errors. So we need to factor in time. The derivative is really simple. Current error minus previous error. Where's the previous error, you ask? Let's add this term first, the derivative, multiplied by the d gain. Then we store the current error as the previous one. We save this error for next time. When the function runs again, it becomes the previous error. Simple, right? Let's restart from the beginning. We add a bit of I controller, then add some D. You'll notice the oscillation gets smaller. Nice. The oscillation is smaller, and it reaches our target pretty quickly. Now, let me introduce a concept. At this point, you'll want to try playing with the PID values yourself to see what gives a good result. Just click on the screen, and the target value will change. You can move it up and down, make it bounce around. The blue line will chase the target. You can tune it well or tune it poorly. For example, if we set the I controller too high, you'll see it oscillates wildly, just shaking all over the place. See it shaking like that. So how do you know what's well-tuned versus poorly tuned? Here, let me introduce another concept. The concept is called simulation. What is simulation? When tuning controllers, many experienced engineers will tell you, tune P first, then I, then D. But I think tuning a controller almost feels like its own field of study. Before you've learned how to tune controllers, these numbers mean nothing to you. So how do I help you get a feel for these values quickly? That's where simulation comes in. Every time I adjust a value, I need to restart. And it takes over 10 seconds before I can tell if the value is good. Then I adjust again, restart again, adjust again, resimulate. You'll find that every adjustment takes 10 seconds, 20 seconds, 30 seconds. Like earlier, it took over 80 seconds to see a stable state. Then you adjust again, restart again. Every single change takes 10, 20, 30 seconds. Like before, it took 80 plus seconds to see stability. Can I see the result in just 1 second? Yes, I built a quick simulation for the first 10 seconds. Every time you change a value, it instantly shows you the first 10 seconds. So you can immediately feel the impact of each adjustment. For example, when I adjust the P gain, see, let's first reset everything to 0. Let's see how each controller affects our system. You'll notice when we start increasing P, we quickly reach our target value. For example, look, originally it would take around about 3.5 seconds to reach the target. But when I increase P, it reaches the target in about 2 seconds. But beyond that, it can't go any faster. Why? Because the output has an upper limit. Just you'd need 10 or 20 seconds to reach 100. There's a limit to this adjustment. Some engineers will say, push P to its limit first, where it can't go any faster. Then, if we simulate 30 seconds, the value still doesn't reach the target. That's the steady state error. Now, we give it a little I, a tiny bit of I. With some I, it slowly approaches our target. But don't give too much, or you'll see oscillation, right? It never converges. It keeps diverging outward because the accumulated I value can become very powerful over time. We usually keep I very small, small enough to eliminate the error, but not so large that it diverges. Then we adjust D. We don't want it to overshoot and swing 2 or 3 times. D reduces oscillation. So we add a little D. And you'll notice the convergence is really clean and smooth. No matter where the value starts, it converges beautifully. Okay, now let's turn off the simulation and reset the values. You'll see it tracks really nicely. Through simulation, you can quickly understand what each parameter in the PID controller does. You'll get a feel for how tuning PID actually works. I'll also mention, in this modern era, we rely on fast CPU to That's all for the basics of PID controllers.